we are writing rigid body aircraft equations of motion. We already wrote the force equation yesterday, and we are halfway through writing the moment equation for the rotational motion of the aircraft. So, we are first writing the equation of motion for this elemental mass and then integrating it for the whole body. Earth is our inertial frame of reference. This E subscript is for Earth. And this velocity of the center of mass is Vc. And we arrived at an expression for the angular momentum for this elemental mass m. We dropped this term saying that all the distances are being measured with respect to the center of mass, and then we arrived at this expression. This omega b is the angular velocity of the aircraft, right, with respect to the body fixed coordinate system. Right. So, P is the roll rate, Q is pitch rate, R is yaw rate, and later on we expanded this, right. So, we found the component of this angular momentum vector about aircraft body fixed x, y and z axis. right. In the event when we assume that this delta m is very small, okay, this summation will become an integral, and then you can write these components as moment is nothing but the rate of change of angular momentum, and using that now we are ready to write the aircraft equations of rotational motion. Because the body is rotating, all the vectors as seen from the inertial frame will have rate of change of vector as seen from the inertial frame will have two components, right. One will involve the angular velocity of the body, right. So now with these information available, I can directly write down now the equations for the moment about 3 axes of the aircraft. Let us assume that aircraft has a symmetry about xz plane. YZ. Okay. So now I am writing the equations about the 3 axes of the aircraft. L is the rolling moment, right. We have been using L prime, so I will put a prime there. So sum of all external rolling moments, right, equal to and I also said that I am going to assume the symmetry about the xz plane, and that too will give you this, right. So, if you find any mistakes with the equations, just stick to this. Okay, you have to use this, okay, and this to arrive at the equations. So, if there are some minor mistakes with these subscript, you can figure that out, right. An assumption which is a valid assumption, right. So, but there could be minor manufacturing asymmetry. So, if you want to take all that also into account, then you have to write the expanded version of the equation. We can also assume that the principal axis system is coinciding with the body fixed axis system of the aircraft, right. So, body fixed or aircraft body fixed axis system is also the principal axis system, right. In that case, we can also get rid of these coupled inertia terms, right. So, you can drop out this cross coupled inertia terms can be further dropped from the moment equations assuming that the aircraft body fixed axis system is coinciding with the right. and finally I am going to retain the equation after getting rid of this coupled inertia terms to there is another access system about which these cross coupled terms will disappear, right. You how do you neglect this part? We assume that no, y is same on in the positive side and the negative side, right. Yeah, that was symmetry. So you can assume another symmetry, right. And which is kind of valid assumption, and it simplifies things to a great deal. No, we are going to look at simpler models. Okay, so you have the equations for the force equations and the moment equations, right, for the translational motion and the rotational motion. Anything else? You also want to find out the location of the aircraft, right, and the orientation at any point in time, right, with respect to the inertial frame. So you want to say where your aircraft is located, right. So you also need to write what is known as equations of kinematics, right. So and that is also changing in time. So we should get the differential equations, right. Orientation or the attitude can be found by using the angles which are called Euler angles, right. So I am measuring the distances from the earth fixed coordinate system, right. So coordinate of airplane at any point in time, right. So let us assume that the aircraft fixed body, okay, aircraft body fixed axis system is coinciding with this earth fixed axis system to start with, right. We can assume that. So we have and right. So it is coinciding with the earth fixed axis system to start with, right. Now I want to know the attitude of the aircraft with respect to the system, right. So there is a rule which says that in order to find the orientation, what you should do is you give a first rotation to the body fixed axis system about this z axis, and that is yaw, right. So there is a rule. So 3 is the first rotation about the z axis, and z axis is at this time is coinciding with the body fixed z axis, earth fixed z axis, right. So 3 is the rotation about the z axis, and this z axis is z axis of the body or the earth, right, because to start with is coinciding, both of them are coinciding with each other. So this z is right. So the second, now you go to a different axis system, right. Once you have rotated your plane yard, right, about the z axis, you will go to a different coordinate system, right, because x and y are going to be different from what you see here, isn't it. Give the second rotation theta about the y axis, and that y axis is indeed the y axis of the aircraft, because I am rotating the aircraft, right. So rotation theta about the new y axis, right, and the final rotation is rotation phi about the second new x axis, right. So remember this rule, okay. What we are essentially doing is we are rotating the aircraft, right, with respect to this inertial frame of reference. You will see what we get from doing. So first rotation is this yaw, right. So so the rule is that you are trying to actually rotate the earth fixed system so that it coincides with the aircraft body fixed axis. So finally the final axis system that I get by doing this should be the aircraft body fixed axis system. I will call this y1 and x1 and this rotation is about the z axis. So, z axis is into the board and coinciding, right. Z E and Z1 both are same. So, I am writing cos psi as this C of psi. Okay. And if you want to write it other way around, then you just have to invert this matrix, and this matrix has a special property. Okay, it is a orthogonal matrix, right. You speak loud, okay, I did not hear you. So, this matrix I can call this as, no, you can also call this as R3. So, rotation about the third, I will call this as R3, let us say, right. So, this matrix has a very interesting property, and that property is this. Right, transpose of this matrix multiplied by this matrix is the identity matrix, right, and that is the orthogonality property of this matrix. So, I can directly write this matrix now. It is not difficult to write this matrix once you know this property. Okay. Now, this next rotation, this theta is about the new y axis, which is y1, right. So, the rotation is about y1, so y2 is going to be y1, right. Okay, so repeat that exercise, and you can find out Okay, so quickly let's just this is R2 and the final rotation is about this x2 axis, right. So, x2 is the body fixed x axis, right. Clear, right. Now, what I want to find out is the relation between this axis system and the earth fixed axis system, right. That is what is going to give me the relative orientation of the aircraft with respect to the initial frame of reference, and this into x1 y1 z1 that is r2 into x2 y2 z2, right. So, if you have to take the derivative of this to find out the location of your aircraft center of mass, right. You want to find out the location of your center of mass of the aircraft at any time t, or u v w are velocity of the aircraft, right, along x b, y b and z b axis. So, another 3 equation, right, we already wrote 6 equations earlier plus 3, now we have 9 equations, right. So, so far we have written the equations only for knowing the location. Now, I want to know the orientation, right, and orientation is also going to evolve in time. Yeah, you should try this out, you will get this. Yeah, so work that out, it is little more complicated, that but you will get this finally, right. So, what he is asking is why I have not taken the derivative of these angles with respect to time while taking the derivative of this, that is what he is asking, right. You should work this out and you will find that you will arrive at this answer. Okay. So, I can quickly also give you an expression for the attitude dynamics. So, let us say we have a vector of angles. Okay. So, there is a small change in all the angles of the aircraft about the earth fixed axis, right. So, the way we have used this 3 to 1 rule, you can write this small change in attitude of the aircraft from the initial earth fixed condition. So, let us call this angle some angle and there is a vector, right. So, aircraft has just changed its attitude by small angle. So, I will write this b for the body and it is a vector. So, this is equal to the first rotation about the k or the unit vector k attached to the earth fixed z axis, right, plus delta theta attached to the new j1. j1 is the unit vector along new y1 axis. Finally, delta phi, which is about the x axis of the aircraft itself, right. So, we can write it new x2 or xb, right. B is for body of the aircraft, right. So, unit vector along x axis of the aircraft, right. All right. Now, you take the derivative of this with respect to time, or I divide it by time delta t, this is going to give me a rate of change in the attitude, right. And take the limit, right, when this delta t becomes small, then it will give you the rate, right, rate of change of angle. If you take the limit, so right, what is this quantity? Rate of change of angle of the body in the body fixed axis system, right. So this is related to the angular rate or the angular velocity of the body, right, or the aircraft. So this is PQR, right, equal to one thing you have to remember that these unit vectors are not along any one fixed axis system, right. There are three different axis system. This K is, right, the unit vector along earth fixed z axis, right. J1 is unit vector along y1 axis, which you obtain after the first rotation, right. So now I have to find, I have to write them all in one axis system, right, that is the body axis system, right, because I am trying to balance out this PQR with the rate of change of theta, psi and phi. You get this? Now I have already given you the transformation matrices, right. If you have followed what I have done, then it will not be difficult for you to figure out that this is equal to Okay. So, finally, we find a relation between the rate of change of attitude angles and the angular velocity of the body. Okay. We want the differential equations for these angles. So, I have to invert this matrix, right. PQ are the variables, state variables of the aircraft, equations of motion. So, I want this to be on the right left hand side, right. Right. So, we have completed writing down the equations of motion, right. So, how many now? 3 plus 3 6, 3 force equations and 3 moment equations, right. So, we have in all 12 equations, and what we are intending to do is we are trying to study the aircraft motion and the dynamic stability of aircraft, right. So, we will continue from here in the next class.